Hello my dear students. So in my last class I was explaining about Heisenberg's uncertainty principle and the explanation which was given for Heisenberg's uncertainty principle. So that is, if we consider a photon which incidents on a particle, suppose if the particle is of reasonable size, what happens? So its position or velocity will not be changed. Okay, suppose if it is a big particle, so that the incident photon cannot act or cannot imply any action towards that particle. So the position or velocity will not be changed by the impact of light photons. So hence it is possible to know exactly both the position and velocity of the particle. So in this way we observed a picture or a figure which clearly explained the change of momentum and position of the electron on impact of photon. So here we made clearly two distinguishable points. So that is, first one, as I said, if the particle is of reasonable size, then its position or velocity will not be changed by the impact of light photons. Whereas when the particle is extremely minute, very small, if the particle is of size of electrons, just imagine the size of an electron, then what happens when a photon falls upon it or comes in contact with an electron? It will suffer a change in its velocity. That means, so the smallest particle, the extremely minute particles like electrons, so when they come in contact with the photon or the impact of a photon will cause a suffer or a change in its velocity and path due to the impact of the photon of light under or used to observe it. Okay, so in this way, so the explanation for Heisenberg's uncertainty principle was given, and later on we also understood the significance of Heisenberg's uncertainty principle, just like how the de Broglie's hypothesis gives us the information that so Heisenberg's uncertainty principle holds good for all the objects, but it is of significant only for microscopic particles. That means that so Heisenberg's uncertainty principle can be justified or can be understood in a better way when we consider microscopic particles. Obviously, the energy of the photon is insufficient to change the position and velocity of bigger bodies. For example, the light from a torch falling on moving ball in dark place neither changes the speed of the ball nor its direction. So this is where we stopped in our previous class. And in this session, let us understand, let us move little forward in quantum chemistry, that to especially quantum physics, to understand what is meant by sinusoidal wave equation. I hope this you have already studied in physics. So sinusoidal wave equation, what it is meant by sinusoidal wave equation. The electric and magnetic fields associated with electromagnetic waves are called as sine waves. Okay? So the electric and magnetic fields associated with electromagnetic waves are sine waves, and the Schrodinger wave is closely connected to the sine waves. So this is a demonstration of a wave or a sine wave. So here we can observe the amplitude of the wave, wavelength of the wave. Okay, so we can study the amplitude and we can study the wavelength and also the distance. So as I said, the Schrodinger wave is closely connected to the sine waves. Now let us consider the motion of a wave in a particular direction. A wave is moving in a particular direction, say for example towards x axis. At any time t, okay, so at any time t, the upward displacement of the wave is represented by y. Let me represent it by y. Next, so if the function of x and time t, so that is by considering all the factors, that is a Schrodinger wave which is moving towards the x axis at any time t, okay, and the displacement of the wave which is represented by y, small letter y, which is the function of x and time, is given by y is equals to f of x comma t. Okay. A sine wave which is travelling in direction with the velocity v and wavelength lambda and frequency nu and amplitude a is described mathematically by sine function as follows. So here, so this is an expression, mathematical expression, which gives us the information of a sine wave which is travelling in x direction with the velocity of v and wavelength of lambda and frequency nu and amplitude a, which is described as y, which is equals to, so there is a correction in this equation, so please observe it properly or else keep your textbook in front of you. So y is equals to a sine 2 pi divided by lambda into x minus vt. Okay, so here lambda is missing and also here the bracket and subtract sign is missing, and this has to be 2 pi. Y is equals to a sine 2 pi divided by lambda into x minus vt. Or else this equation can also be written as or simplified as a sine, I can take 2 pi as common. Okay, so 2 pi is taken as common, a sine into 2 pi into x minus vt or nu t divided by lambda, where nu is equals to v divided by lambda, and here y is called as a wave function. Okay, so this y is called as wave function, and this equation tells about the displacement y at any point x and at any time t. So if we understand the basic concept of chemistry, like if we study the structure of an atom, so we know that the most probable place where an electron can be located or observed, so that is what is called as orbital. So mainly there are 4 different orbitals like s orbital, p orbital, d orbital and f orbital. So in quantum chemistry, depending upon where exactly the electron is observed or where easily it could be found out, so we are going to classify them based on the quantum numbers. Okay, so the quantum numbers like principal quantum number, azimuthal quantum number. So there are many different ways in which we use Schrodinger wave equation for hydrogen atom, which yields different quantum numbers like principal quantum number, azimuthal quantum number, magnetic quantum number and spin quantum number. So in this way, so here the electron or a particle, okay, so which moves in a wave and which is travelling in x direction with certain amount of velocity and certain amount of wavelength, that is lambda, and frequency nu and amplitude a, is described using sinusoidal wave, and this is how we are going to express a sine wave or sinusoidal wave with respect to a mathematical expression. Okay. So any equation having the characteristics of a sine function is called as a sinusoidal wave function, and this is the figure which gives us how a sine wave or sinusoidal wave is going to be propagated in a direction. So that direction might be particularly towards a x axis or irrespective of the direction. A sine wave always it moves in a direction, in one direction, with the velocity, with a wavelength, with a frequency and with the amplitude. So this is how we understand. So this distance, so this is measured as amplitude, and the distance between these two is measured as wavelength. Okay, and this, the upward and downward movement of the wave, this completes one cycle. Okay. So this is how we are going to understand sinusoidal wave function. And next what we have to understand is operator. What is an operator? An operator is a mathematical instruction or procedure to be carried out on a function so as to get another function. the result of an operator on a function gives another function. Say for example, operator into function, this gives rise to another function. So here this equation does not mean that the function is multiplied with operator. Okay, so that is why I said operator and function which gives rise to another function. Okay, so here it does not mean that the function is multiplied with operator. The function on which operation is carried out is called operand. Okay, the function on which operation is carried out is called as operand. So a mathematical operator such as f, okay, so f we use f of x, like that we use a mathematical operator such as f, d by dx or square root etc. are always accompanied by a mathematical quantity or a mathematical function upon which it operates. For example, in square root of 3, square root is a mathematical operator and 3 is a mathematical quantity on which it operates. An operator written alone has no significance. If you write just a square root, it does not have any significance. So definitely there should be a mathematical operator along with that mathematical quantity, then only it will get a meaning. Otherwise an operator which is written alone, it does not have any significance. Understood? And next is, let us take an example. So here dx to the power 5 divided by dx, which is equals to 5x to the power 4. So here d by dx is an operator, x raised to 5 is an operand, and 5x to the power 4 is the result of the operation. Okay. So in this way we are going to understand this expression. So this mathematical expression means that here dx or d divided by dx is the operator, x raised to 5 is the operand, and 5x4 is the result of the operation. Next is a Laplacian operator. So here we have introduced a new term. Okay. So this might be new for B.Sc students, but not for PCM students. So this is reverse of delta, right, and this is called as del. So del is a very common differential operator used in quantum mechanics, okay, which is called as a Laplacian operator, So it is represented by the symbol del. Okay, so this is called as del. This is a very common differential operator which is used in quantum mechanics, and it is defined as del is equals to delta divided by delta x plus delta divided by delta y plus delta divided by delta z. Okay. So the meaning of this del is this. So we are writing this whole term in short form, or represent it in a short form by using a symbol del. Del means so delta divided by delta x plus delta divided by delta y plus delta divided by delta z. So this is a differential form. So we are making it simple. Okay. So why we are studying all these things? Why we are understanding what is an operator, what is an operand, or what is an Laplacian operator or Hamiltonian operator? So all these are used to understand Schrodinger wave equation. So we are going to use all these factors there. So if we directly go to the Schrodinger wave equation without knowing what is meant by operator, what is meant by Laplacian operator, what is meant by Hamiltonian operator, or what are eigenvalues or eigenfunctions, so it is very difficult for us to understand Schrodinger wave equation. So for that reason, so we should know what is this del means. And the next is so the square of operator, that is del square. Okay, so del squared is called as a Laplacian operator. Okay, so this is del and this is del square. So del square is called as a Laplacian operator, and which is defined as so del square is equals to delta square divided by delta x square plus delta square divided by delta y square plus delta square divided by delta z square. Okay, so in this way we are going to represent a Laplacian operator. And the next is a Hamiltonian operator. The operator which corresponds to the total energy of the system written as a sum of kinetic and potential energies is called as an Hamiltonian operator. Okay, and it is represented as H cap. So, there is a cap. So, this has to come just above this H. Okay, so, in that way we are going to represent or symbolically represent Hamiltonian operator. What is an Hamiltonian operator? So, the operator which corresponds to the total energy of the system written as a sum of kinetic and potential energies is called as Hamiltonian operator. The total energy of a single particle of mass m is given by, so H cap is equals to minus H square divided by 8 pi square m into del square plus del. Okay, so del square plus del. So, where del square is the Laplacian operator of a particle. Okay, so this is what is Hamiltonian operator. And next is eigenvalues and eigenfunctions. So, Schrodinger wave equation, being a second order differential equation, can have a number of solutions for the amplitude functions. Some of these values are imaginary while others are real values. The imaginary values are not accepted, only those values of y which give definite and acceptable eigenvalue of the total energy E of the electron are acceptable. Okay, so, the acceptable values of the wave function y are called eigen wave functions, because we can accept. So, they are not imaginary values, but they are real values. The imaginary values are not accepted in case of Schrodinger wave equation. Only those values of y which give definite and acceptable value of the total energy of the electron are acceptable. The acceptable values of the wave function y are called eigen wave functions, and the value of E, that is the total energy, the value of E means here total energy, is given by particular eigen wave function which is called eigenvalue. Okay. So, this is what is eigenvalues and eigenfunctions. Next is a very important thing what we have to concentrate in this session, that is a Schrodinger wave equation. Okay. So, it is pronounced as a Schrodinger, not Schrodinger. It is pronounced as a Schrodinger wave equation. So, he is Erwin Schrodinger in 1926 gave a wave equation to describe the wave behavior of electrons in atoms and molecules. So, we all know that moving electrons behave both as particles and as a wave. So, this we have already proved or understood by studying de Broglie's wave hypothesis, that is the dual nature of electrons. The moving electrons behave both as particle as well as a wave. If the electron behave as wave, then there must be wave equation to describe their behavior, right. Suppose if the electron behaves like a wave, then we should have a wave equation to describe their behavior, just like how we understood the behavior of a particle by considering sinusoidal wave equation. So, at the beginning of this session we understood what are sine waves, how the sine waves are going to propagate, right, and what is the mathematical expression of a sine wave which is travelling in x direction with the velocity v and wavelength lambda and frequency nu and amplitude a. We deduced a mathematical equation. In the same way, if an electron is considered as a wave, then there must be wave equation to describe their behavior. So, for this purpose, Erwin Schrodinger in the year 1926, as I said, he gave a wave equation to describe the wave behavior of electrons in atoms and molecules. The Schrodinger wave equation for an electron wave propagating in 3 dimensions in space is written as follows. So, this is what is called as a Schrodinger wave equation. So, the equation says that, so del square psi divided by dx square plus del square psi divided by dy square plus del square psi divided by del z square plus 8 pi square m divided by h square into e minus v psi, which is equals to 0. Okay, so the whole term is equals to 0. And let us call this equation as equation number 1, and this equation number 1 is the Schrodinger wave equation for an electron propagating in 3-dimension space. So, now let us understand what are these terms, what does these terms mean. So, in the above equation, psi is equals to the amplitude of wave function. So, here we have introduced a new term or a new symbol, and this is what is called as psi, PSI, and it is pronounced as psi. Okay. So, the PCM students are very much familiar about this. So, this is for B.Sc students, and this is called as psi, PSI, and it is pronounced as psi. So, what is psi here? So, psi is the amplitude of wave function, and this x, y and z are the 3 coordinates, and m, okay, so m is the mass of the particle, v is the potential energy, and E is the total energy of the particle. Okay, so these are the terms. Suppose if the question asked in the exam, so write Schrodinger wave equation for an electron wave propagating in 3 dimension in space and explain the terms. So, then you have to write this equation and explain all the terms, saying that psi is equals to the amplitude of wave function, x, y and z are the 3 coordinates, m is the mass of the particle, v is the potential energy, E is the total energy of the particle. Okay. So, this Schrodinger wave equation can also be written as, so del square psi plus 8 pi square m divided by h square into E minus v psi is equals to 0, and let me call this equation as equation number 2. Okay. So, in this way we can also represent Schrodinger wave equation. So, here del square is called as an Laplacian operator. So, del square is nothing but Laplacian operator, and this is the value of del square. Okay. So, this is Laplacian operator. So, multiplying equation 2 by h square divided by 8 pi square m. So, by multiplying equation 1 by h square divided by 8 pi square m, we get h square divided by 8 pi square m into del square psi plus E minus v into psi, and this is also equals to 0. By rearranging this equation, how I am going to rearrange? I will take this E and psi as common towards the right hand side. Okay. So, if I take this towards the right hand side, and what is left is so minus h square divided by 8 pi square m into del square plus v into psi is equals to E psi. Okay. So, this is what is left. So, the whole term, that is minus h square divided by 8 pi square m into del square plus v into psi can be represented as E psi. So, what happens to this equation? So, this can be represented as h cap, just like how we have seen in the previous slide. Okay. So, in this slide, so h cap is equals to minus h square divided by 8 pi square m into del square plus del. Place this into h cap, then what happens? So, I am going to get h cap psi is equals to E psi. Okay. And this equation 3, so I will call this equation as equation number 3, and this equation is the simplest form of Schrodinger wave equation. Okay. So, this is the simplest form of Schrodinger wave equation. And as I said, so here psi is the wave function of the system which describes the state of a system, and if psi is independent of t, then it corresponds to the state of a system with specific energy. The Schrodinger equation can have number of solutions or wave functions. All the solutions are not acceptable. Okay, so all the solutions are not acceptable. The acceptable wave functions must satisfy the following conditions. So what are those conditions? So the wave function must be single valued and finite, that is, for each value of the variables x, y, z, there is only one definite value of the wave function. Next, second one, the wave function must be continuous, that is, there must not exist any sudden changes in wave function as its variables are changed. Okay? And the third rules is for bound states, that is particle having a definite energy, so psi must vanish at infinity. That means it should become 0 at infinity. If psi is a complex function, then psi into psi star must vanish at infinity. So satisfying the above conditions, Schrodinger equation yields significant solutions for certain values of the total energy E. So these values are called as eigen values. Okay. So these are some of the conditions which has to be followed by or accepted by wave functions to understand the Schrodinger wave equation, which can have number of solutions or wave functions. Okay. So then only if the particle or if an electron follows all or satisfies all these following conditions, so then only so it is acceptable, that is the value of Schrodinger wave equation or the solutions are acceptable, otherwise they are not acceptable. Okay. So this is how we are going to understand Schrodinger wave equation. So I am going to stop it here, and in my next class we will understand what is the significance of wave function, that is psi and psi square. Okay. So thank you dear students.